This is video 19 in our series Topics in Tensor Analysis. In this video, we're going to derive the Chistoffel symbols in terms of the cylindrical coordinate system. Now back in, I think it was video 17, we had derived this equation and introduced the concept of Chistoffel symbols. And then in the previous video, number 18, we derived this equation that shows the relationship between Chistoffel symbols and metric tensors. What we'll do in this video is determine the Chistoffel symbols in coordinates, cylindrical coordinates, by using our basic equation here. Then in the video after that, we'll once again determine Chistoffel symbols in cylindrical coordinates by using this expression. Now, just to remind ourselves, here is a cylindrical coordinate system. We have Cartesian axis, x1, x2, and x3. Then we have some point in space with a position vector r, and we drop a perpendicular down to the x1, x2 plane, and then we consider the distance from the origin and the angle that this makes with the x1 axis. And for this Cartesian axis, it has a unit vector z, so this distance going up can be z. So the cylindrical coordinates are psi, rho, and z. Consequently, the position vector r can be written like this. Now, in our definitions, we have it set up so that the coordinate axes are labeled as these with a numbering system. J goes from 1, 2, 3, and further on out if we have higher dimensions than just a three-dimensional space. Same thing for here. So we will we'll call rho will be U1, psi will be U2, and z will designate as U3. I want a reminder that the playlist for all the videos is at the website, digital-university.org. Okay, so we have, this is the position vector r in terms of cylindrical coordinates. Now remember, up here in the numerator, these are tangential vectors, and they were obtained by taking the partial of r, the position vector, with respect to the different coordinate axes. That is, I equals 1, 2, 3. So when I equals 1, it's u1. So we've taken the partial of r with respect to rho, and that will give us e1, or that would be designated as e rho. Then when I equals 2, we're taking the partial of r with respect to u2, that's psi, and then that will give us e2, or e psi. And then when I equals 3, we're going to be taking the partial of r with respect to z, and that will give us e3, or ez. So taking the partial of r with respect to rho just gives us cosine plus the sine, and that's what we have right here, and that is then e rho. Taking the partial of r with respect to psi, this will be minus sine plus the cosine, and that's what we have here, and then that's equal to the tangential vector e psi. Then when we take the partial of r with respect to z, that's just going to be 1 times the unit vector k, and that will be e3, or ez. So e sub z is just the unit vector k. So we have 3 tangential vectors here, here, and here, or this would be E1, E2, and E3. Now, what we want to do is take partial derivatives of these. And that's not what we want. We want this one. Okay, we had I equal 1, that will be E rho, right here. Then J equals 1, 2, and 3. So we have U1 was rho, U2 was psi, and U3 was z. So I equals 1, that is E rho. Then we take the partial of that when J equals 1, 2, and 3. So we're going to take the partial of this. We can keep it in focus. Okay. We'll take the partial of this with respect to rho. Then we'll take the partial of this with respect to psi. Then take the partial of this with respect to z. That's what this means for when I equals 1, or that would be E rho. Well, the partial of this with respect to rho is 0. The partial of this with respect to z is 0. So of the three derivatives that we take, only one of them is non-zero. That's when I take the partial of this with respect to psi. So what we have then is partial of E rho with respect to psi. And this will be minus the sine plus the cosine. So that gives us this expression. Then let's see. We look at this. Does this look familiar at all? Here, minus sine plus the cosine. And that would be, just a second, let's look at this more carefully. Yes, here. Minus sine plus the cosine. So if I had this divided by rho, that'd be minus the sine plus the cosine. So this is equal to 1 over rho times E psi. Now we want to take partial derivatives again. I will equal 2. Then we have J equals 1, 2, and 3. When I equals 2, that's E psi. So now we're going to take the partial of this with respect to rho. That will give us a non-zero answer. Then take the partial of this with respect to psi. That will give us a non-zero answer. Then take the partial of this with respect to z. That will just be 0. So of the three derivatives that we take, 2 of them give us non-zero values. So let's take care of those real quick. We have partial of E psi with respect to rho. And that would just be minus the sine plus the cosine. Same thing as what we had up here. Minus the sine of psi plus the cosine of psi. And this equals 1 over rho E psi. Now I want to take the partial of this with respect to psi. So taking the partial of this with respect to psi, the partial of the sine is the cosine, so you have minus rho cosine. This is minus sine, so you have minus rho sine. So minus rho cosine minus rho sine. So let's write that out. Minus rho cosine psi I minus rho sine psi j. And let's see, if we factored out minus rho, that would give us cosine plus sine. And that's what this is, e rho. So this is equal to minus rho e rho. Okay, now we have to take partial derivatives of this, but this is just a constant, so all those derivatives are going to be 0. So we took partial derivatives when this was equal to 1 and varied this from 1 to 3. Then when this was equal to 2, varied that from 1 to 3. And then when this is equal to 3, all the derivatives were 0. So we have, when we take all those derivatives, we have 3 non-zero expressions right here. This is equal to this is equal to this, and this is equal to this. So what we're going to do is write these at the top of the board after we make some space. So let's do that real quick. And also, let's not forget now our basic definition. We have that, or our basic relation, I should say, partial of EI with respect to UJ equals gamma IJ times one of the basis vectors with a summation index. And then we had 3 equations. We had the partial of E rho with respect to psi, and that was equal to 1 over rho E psi. Then we have the partial of E psi with respect to rho. That will equal 1 over rho E psi. Then we have the partial of E psi with respect to psi, and that's minus rho E rho. So these are the 3 equations that we had derived. Reminder now that rho corresponds with U1 and psi with U2, and there is no expression involving z. Okay, so let's look at this one. We have partial. What we're going to do now is put these back into the numbers. So here we have E rho, that corresponded to 1. E. Then with respect to psi, but psi is U2, and that equals 1 over rho E psi, that's E2. So this is just this, putting these subscripts now from letters back into numbers. So we have this equation. But now here, we can write this using Chistoffel symbols. We would have gamma 1, 2. Then we'd have one of the basis vectors with the repeated index equals 1 over rho E2. Now on this side of the equation, here we have E2. We can write the same thing on this side then, just let K be equal to 2. Then that implies that gamma 1, 2, 2 equals 1 over rho. So there we have determined then one of our Chistoffel symbols. And let's write it just up here. Gamma 1, 2, 2 equals 1 over rho. Now, for this one, this also equals 1 over rho, equals E psi. So does this give us the same kind of Chistoffel symbol? Let's see. Here we have partial. Putting these back into the numbers now, E2, that corresponds to 2. With respect to rho, rho is U2, equals 1 over rho E2. And no, rho is 1. That's a mistake. Psi is 2. Okay, now let's put this a bit better focus. Here we were working with this expression, putting it back into numbers. That's 2. Rho, that's U1, that's like this, equals 1 over rho, and psi, that corresponds to 2. Now we can write this in terms of Chistoffel symbols. We'd have gamma 2, 1, 2, 1 times one of the basis vectors with the repeated index equals 1 over rho E2. Well, here on the right side, this is 2, so let's put it in here. Specifically, write it like this. Then that implies that E212 equals 1 over rho. So we had gamma 1 over 2, 2 equals 1 over rho. And now we have gamma 2, 1, 2 equals 1 over rho. And this is consistent with the last video. In the previous video we showed that if we have two gammas and these are switched around like this, they have the same value. And indeed it came out to be the same value. Now we have one more to determine, and that's this. We have the partial of E psi with respect to psi equals minus rho E rho. Putting this back into numbers now, with our numbering system, this would be E2. With respect to psi, that's U2. Equals minus rho E1. Rho corresponds to 1. When it's used as a subscript here with our labeling, labeling the tangential vectors. So here we have this equation, just putting this into the numbers now with our numbering system. So if you want to write this down in terms of Chistoffel symbols, we'd have gamma 2, 2, E with the repeated index here, equals minus rho E1. Well, here, this is 1, so let's make it 1 on this side too. So we have specifically then, this implies that gamma 2, 2, 1 equals minus rho. So here then are Chistoffel symbols for cylindrical coordinates. There are 3 of them, the rest would be 0. So that's it for this video. What we'll do in the next video is again determine these only using this equation. And usually when we want to determine what Chistoffel symbols are, it's more common to use this approach than to use this approach. So come back and join us for the next video. We'll use this method and once again redetermine the Chistoffel symbols for cylindrical coordinates.